Hello everyone, my name is Philipp Holzinger and I will present Hardening Java's access control by abolishing implicit privilege elevation. This is joint work with Ben Herrmann, Johannes Lerch, Eric Bodden and Mira Mezzini. So Java has been around for about 20 years and it is one of the first platforms that was specifically designed for the secure execution of untrusted code. However, as Cisco's annual security reports show, it is also one of the top attack vectors for web exploits. And we really want to understand what contributes to Java's insecurity so that we also learn for the secure design of other systems as well. Before we dive into the details of our study, let's have a brief look at the basics of the Java security model. The timer doesn't work, by the way. Thanks. I just gained a minute, thanks. So the Java runtime environment executes applications, and on a high level it comprises two components. On the one hand, it's the Java virtual machine, which provides basic functionality for program execution, including just-in-time compilation, memory management, and other basic functionality. And on the other hand, it comprises the Java class library, which is mostly implemented in Java. And it's a collection of a large number of system classes that provide common functionality, like print stream print, for instance, or random next int, and many other commonly used functionality. Besides non-security sensitive functionality like print and next int, there is also security sensitive functionality like file system access, like file delete in this example here, which should be restricted to make sure that untrusted code cannot use such functionality to harm our host system. So applications are free to call the non-security critical functionalities. Once they call a security critical functionality like file delete here, something special happens. So the security critical functionality will consult the security manager in the class library to check if access to this sensitive functionality shall be allowed or not. So the security manager is in charge of deciding whether access shall be granted or not. So how does the security manager decide this? For this, it uses stack-based access control. What we see here is a simple example of a short call stack of an application that attempts to delete a file. So when the security manager, the first thing we do is we assign permissions to our code. As we can see here, classes that belong to the Java class library, like file and security manager, are always assigned all privileges automatically, which is here indicated by the green checkmark sign. We can, however, assign privileges to code of application classes using a customized policy file. In this example here, we decided to grant no privileges to our application code at all to make sure that it is securely contained and cannot harm our system. So when now the security manager is being asked to to grant or deny access to the file delete functionality, it will perform a stack walk. And a stack walk is simply checking for each and every caller on the call stack if every caller is assigned appropriate privileges for the desired functionality or not. In this example here, we will see that the check walk will see that the security manager and file delete are both system classes and thus assigned all privileges. But at this point, it will see that untrusted, the class of our application here, has not been assigned appropriate privileges. And in this example here, access to the delete functionality will be denied. So this is how basically access control in Java works. And what we keep in mind now is that sensitive methods in system classes are guarded by permission checks. Now, until this point, this is very well known, and this is how the security model is supposed to work. What we find in our study is, however, that there is a deviation from this model, which is basically implicit privilege elevation. Consider, for instance, this hypothetical example here. Consider that, just suppose that this is a system class here. This system class has two methods, openFile and getPublicLock. The openFile method receives a string argument which represents a path to a file, and it just returns a file handle to the file. That's all it does. getPublicLock uses this functionality to get a file handle to log.txt. That's it. Since openFile provides access to the file system, which we consider sensitive, we see that here is a permission check. and the permission check is simply executed by a call to System Security Manager check permission. What we also find, however, is this conditional here. And this is what we call a shortcut, because this conditional here guards the permission check. So under certain circumstances, the permission check will simply be skipped and not executed at all. So in this example that we see here, the shortcut checks if the immediate caller of OpenFile, so the method that calls OpenFile, is part of a system class. And if it is part of a system class, no permission check will be executed. Now, this has interesting consequences. If in our application we implement, for instance, the exact same functionality that getPublicLock implements, then it depends if our code has been assigned privileges or not. If it has not been assigned privileges, access to log.txt will fail, because if we call OpenFile, a permission check will be executed. If instead, however, we call getPublicLock, then getPublicLock will call OpenFile, and since getPublicLock is part of the system class and it calls OpenFile, a permission check will be skipped, and our application will be able to access the contents of log.txt in this way. So this is a bit counterintuitive. So if we do something, it does not work under certain circumstances. However, if we call a system method that does the exact same thing, it always works. So we keep that in mind for a minute. Shortcuts prevent, like I just explained, existing permission checks, depending on certain properties of the call stack. That could pretty much be anything. In the example we have just seen, it's just the identity of the immediate caller. The consequence is that the callers of shortcut-containing methods, like getPublicLock in the example, somehow act as guarantors, which means since their involvement may prevent the execution of a permission check, they have to make sure that whatever they do is also secure, even if called from untrusted code. So that puts them in a certain responsible position. Now, when I presented this to somebody, I was asked why we don't report these shortcuts, because they are apparently bugs and have Oracle fixed them. They are not bugs by themselves. They were implemented intentionally to speed up permission checks, because every stack walk is kind of expensive, and every stack walk that we can skip makes our application faster. So it's not a bug, and also it's not wrong. So it's not giving untrusted code any access that it shouldn't have in the normal case. As I will explain in the following, however, these shortcuts significantly contribute to Java's fragility. The first thing we will consider here are maintainability issues. This is now a real example from Java 7. And as you can see, this method here, checkMemberAccess, performs a permission check. But this permission check is also guarded by a shortcut here. And this shortcut, as you can see here, is a complicated conditional that makes extensive assumptions about the call stack. So in this case here, about the length of the call stack, the order of callers, and also their identity. So as you can imagine, it's very easy to break the assumptions that are hard-coded in this shortcut. And we can find this actually documented in classes that make use of this method. So what we find in source code comments is, for instance, in method handles, this function performs stack walk magic, do not refactor it. Or be very careful not to change the stack depth of this call for security reasons is a source code comment in class. Or in the security manager, if this method is overridden, then a call cannot be made as the default implementation relies on the code being checked at stack depth of 4. So what I'm trying to say here is that the impact of a shortcut at a certain location in the class library has not local implications on the maintainability of the platform, but rather global implications on the maintainability of the entire class library. Besides these maintainability issues, there's also security problems directly enabled by these shortcuts. This is the exact same example of a system class that we've seen before. And now suppose that the developer of a system class introduces a very simple helper method, OpenFile from root. As you can see, this method does nothing, not much. It just takes a string argument, it prepends a slash, and then it uses this argument to call OpenFile. This is a very simple method. It looks sensible, reasonable, and not harmful at all. However, this method introduces a major security defect because it provides unlimited access to the entire file system to all code, even if it has never been assigned any privileges. Why is that? OpenFile is our method here that contains a shortcut, and we know that it skips a permission check if the immediate caller is a system class. So if from our application we call this method immediately, a permission check will be executed. So if we try to access a sensitive file on the file system, a permission check will find that we don't have permission to do so, and access will be denied. If, however, instead we use OpenFile from root, our confused deputy here, and OpenFile from root will call OpenFile for us, then a permission check will be skipped, and our application will actually be granted access to files that it shouldn't have access to. We reviewed a sample set of 48 exploits that were provided by a company, Security Explorations, and we actually found 4 examples of exploits that make use of such confused deputies in a way that we've just seen. So this is not a theoretical problem, it's actually used by attackers to craft their exploits. Now, it would be very easy to blame the developer that originally introduced the confused deputy, right? However, that wouldn't be fair at all, because shortcuts are not visible to callers. So if you don't know the implementation of a system method, you have no means to decide whether it would skip a permission check under certain circumstances or not. Also, just by looking at the signature of a method, you don't know if it would skip a permission check. So it's really hard to decide if your code is affected or not. Also, another API usability consideration is that developers need extra effort to prevent confused deputies. What we usually want is that implementing secure code needs less effort and is easier than actually writing it in an insecure way. We don't find that here. And finally, callers cannot simply refrain from privilege elevation, which violates the principle of least privilege. So there is no way to say, sorry, I don't know what I'm doing. Please make sure that my code is running just with the least amount of privileges to make sure that I'm not accidentally harming the system. Again, no way to do that. So we can confidently say that shortcuts weaken Java's security model in practice. Is there something we can do about this to improve the situation? Yes, there is, luckily. We can move from an implicit model of privilege elevation to a fully explicit model of privilege elevation. So what does that mean? In our example, that would mean that the first thing we have to do is remove the shortcuts. So remove the conditionals that actually prevent a permission check from being executed. And by this, I really mean literally erasing it. So just remove it from the method. Are we done yet? We are not, because as we've seen before, untrusted code before our modifications was able to call getPublicLog and then actually get the contents of log.txt. This was intended functionality before, but after our modification here, this would fail. So that would be breaking backward compatibility. So to retain backward compatibility, we need to modify our callers such that they explicitly elevate their privileges. And there is dedicated functionality in the class library to do that. Now, explicit privilege elevation doesn't suffer from the maintainability and security problems that we've seen before. So this is definitely an improvement here. And we do this to retain backward compatibility. We implemented our proposed solution by using a semi-automatic static analysis approach to locate the shortcuts in the class library in the first place. It's semi-automatic. By semi-automatic, I mean that we automatically search for a candidate list of methods that may or may not contain a shortcut, and we manually select the methods that actually do contain a shortcut. We then manually remove the shortcuts of 32 methods in the OpenJDK 8. And we used an automatic bytecode transformation to adapt all callers that call the methods that we modified. This has to be done automatically because the number of callers is so incredibly large that you just cannot do that manually. It's thousands of callers, and you wouldn't want to do that. Now, we evaluated our implementation first in terms of performance, because as I explained before, these shortcuts were presumably introduced in the first place to speed up program execution. And we found in so we implemented micro-benchmarks executing every method that we modified, I think 115 million times. And we found that the methods that we modified actually had a slowdown of a few microseconds. What we found, however, when assessing the execution speed of real-world applications, we found that these little slowdowns just have no impact on real-world applications. So the real-world applications that we used here is the Da Capo benchmark suite, which comprises a set of open source applications that cover a broad range of possible program behavior, and we found no performance slowdown at all. Backward compatibility is retained, it may be possible that some applications may need adjustments to their policy file, but as we explained in the paper, such adjustments can be done with little effort and even automatically in some cases. So what we can say is that shortcuts can be removed to increase maintainability and security. There's a few general lessons that we learn from this. So on the one hand, if given the choice, you should always go for an explicit way of privilege elevation as compared to an implicit way of privilege elevation, because it makes your life a lot easier. Explicit privilege elevation is much easier to reason about, and it increases maintainability and security. Also, stick to the security model. So the security model, as it has originally been proposed for Java, did not contain these shortcuts. But as we've seen, they weaken the security model in practice. So my advice is, if at some point you realize that the security model that you designed cannot be implemented for whatever reason, let it be performance reasons, then rather step back and rework your model instead of trying to fix your model by tweaking your implementation. This has bad side effects, possibly. Also, properly document your trade-offs. We invested significant effort in actually showing and being sure that the shortcuts that we discussed were actually just introduced for performance reasons and not for any other reasons. If that would have been documented clearly and properly, we could have saved a lot of effort. And finally, re-evaluate your performance trade-offs in regular intervals. After all, you hope to gain something through a trade-off, right? But if you don't gain performance anymore because after 15 years it's just not necessary anymore, all you do is you weaken your system by the trade-off. With this, I conclude my talk, and I'm happy to answer your questions.
Hi there. There's a paper in the Aspelos from Shanghai a couple of weeks ago on the Java, well, essentially on avoiding the confused deputy problem that you might want to look at. This is the cherry architecture that we've been doing with SRI and the University of Cambridge. And so that might be a very interesting alternative to the way you're approaching this.
Okay, thanks for pointing this out.
Yeah.
I will certainly have a look at it. Cool, thanks.
Okay, so I understand that they originally put in shortcuts for performance reasons. Did you actually measure whether that was actually important these days? I.e., if you just remove the shortcuts and do things properly, is Java now fast enough?
So the question is it still fast enough if you remove the shortcuts?
Yep.
Yes. So I think I had a slide on performance measurements, but it wasn't very detailed. So we performed micro benchmarks to measure the effects if you isolate the method that we modified, right?
Right. No, not the method you modified, but if you just told them, hey, get rid of your shortcuts, you don't need the performance.
Oh, you mean removing the entire method that contained a shortcut?
Well, yeah, basically have them do the proper things as they were supposed to do in the first place.
Well, in principle, doable. However, chances are that you break backward compatibility. And backward compatibility has always been valued very, very high. So it's hard to propose something that breaks backward compatibility, even if it improves the system and would be a cleaner solution.
Right. Okay.
Hi, I'm Ethan Johnson, University of Rochester. So my understanding is that Java has been removed from all major web browsers within the last couple of years, or at least last one that still has it is Internet Explorer, and that's still only being retained as a compatibility thing. So do you know of any ever common scenarios where a Java runtime environment is still expected today to run untrusted code?
Mm-hmm. So I cannot definitely answer it. And I also asked the same question. I actually asked Oracle. And also they don't, according to what I heard, they are also not 100% sure where it is not used. But I could imagine that, for instance, in a server context where you're executing several servlets at a time and you want to make sure that they don't influence each other, that might be a thing. However, I don't know to what extent this is actually used or not. So I don't know. And also, I'm not so sure how to find that out, actually. But if you have a source, then I'd be happy to check it.
Thank you.
Okay, let's thank the speaker again.